Okay, so another application is fiber products in the category of schemes. So we spent a lot of time talking about fiber products last semester. Okay, so if so let A and B and B be R algebras. Okay, so the ring, so this thing here, it turns out that we can take the tensor product of two rings, right? Okay, they're both R modules, but it turns out that A tensor B over R, this thing has a ring structure. This thing here, this has a ring structure. It's actually a structure of an R module. An R algebra. Okay. And so one thing I just need to tell you is I need to tell you how to multiply two elements of this. So how to multiply. Okay. So here's how to multiply. If you have so on simple tensors, I'm going to write it out on simple tensors, but you just kind of extend this rule. If I take A1 and B1, and I take A2 and B2, like this, then all I do is I just multiply each of the factors. Okay, so this is what you do. This is how to multiply it. So this thing has a ring structure on it, and you know if you have multiple things, you just kind of distribute and multiply, right? If you're taking linear combinations of these things. So I'm just gonna I just showed you how to do it for pure tensors. Okay, so so what do we do? So okay, so if x if x is spec A and y is spec B, and let's say S is spec R, right? Then so one thing we can do is so we can look at the fiber product. Okay, so we have X. Okay, it maps to S, and this maps to Y in the category of schemes. Okay, and up here we have the fiber product, as you guys remember. So it's this thing here. Okay, so this is the fiber product. So this is the limit of the diagram, which is this thing. And so it turns out that the fiber product here is this thing is just spec of A tensor over RB. Okay, so the fiber product is just the tensor product of the rings. Okay, so so that's really cool. It allows us to do lots of things, right? And lots of geometric things with rings that we, maybe we wanted to do, but didn't know how to formulate. Okay, but and so what's the universal property? Right, is that if you're given a map, given z to y and z to x, a map of S schemes. So this is the analog of an R algebra. So we get Okay, so let me just kind of fill in the diagram here. So if you had Z, and we did this last semester, but let's just do it again. So we had this is over S. And so this thing here, and this, we have two things like this. Okay, and what happens is that this thing gets a free map here. So this is kind of the universal map like this. Okay, so in terms of rings, right? Okay, so if Z is let's say spec C, it says that given, okay, so let's just do everything. So we have C here, and if I have a map from A, so if I have an R algebra map like this, and B, if this is a map of R algebra, so R goes into here and into here. So we had R, this was maybe sigma of B, the structure map here, and this was sigma of A, okay? So, and then we have A tensor over R with B. We have a map into here, we have a map into here. So, okay, so one thing to notice is that this thing in terms of schemes and geometry, right, this is the projection map, the projection onto Y, and this is the projection onto X. Okay, so in terms of algebra, right, this is the inclusion map, right? So this map here is like, we'll call this IB, and IB of B goes to 1 tensor over RB, right? And similarly with IA, A tensor over R1, okay? And then we get a universal map here too. So whenever we're in this situation, we get a map like this, okay? So one thing, so tensor products are really about fiber products, geometrically, okay? And so like, what are some things that we can talk about now that we have fiber products? Okay, so with this notation as above, so one thing that we can do is we can do fibers of a morphism. Okay, so if you know, okay, so let me give it an example. So fibers of a map. Okay, so if F is a map from X to S, so as above, and let's say I don't know, let's say T is a map. T is a map from T. There's a thing from T to S. So here's something concrete to think in mind. So T could be like spec C. S could be spec of C of X. Okay, so and then this map here could be, let's call this map little s. Okay, and S. Okay, so the backwards map from S from here to here is, say, this thing sends X to, okay, I got a better name. Let's call this map 0. Okay, so whenever I have a map of schemes, I'm going to write a little star like this for its ring map. Okay, so we have this map here. Okay, and so then X could, so what this does is then, so this is an example. Then oh, we should maybe call this something. We should call this S. We should call this, I don't know. Yeah, let's call this, oh, okay, we'll call this 0 still. Then F inverse of 0, okay, so this is going to be defined to be equal to the fiber product of the two things. So this is the definition, right? T cross over S with X. So this is how you define the inverse image. So this is the fiber. Okay, this is the fiber of a map, and let me kind of give you the drawing here. If I have the point 0 here, then we're going to pick out this thing. Okay, so this is f inverse of 0. Then we define it to be this fiber product. Okay, and let's kind of like make sure that this makes sense. Okay, so let's do an even more concrete example. So again, what have I done here? So in terms of diagrams, we have this. This goes here, and then we have f inverse of 0, and it sits over t. So we defined this to be the fiber product of these two maps. So this was our given map. This was the point that we had. It really could be any morphism we want, but it's good to think about it like points. Okay, and so so let's take an even more concrete example. Okay, so let's take a really concrete example. So let's go back over here. Let's take x to be, I don't know, a circle or something, or this thing. Okay, so we have this, and then so we need the map f. So here we're mapping to the line here, okay, and so we'll just map, so f sharp. So we need a map from here down to the bottom. So this is the algebra map. C of x. This thing goes into C of xy. Mod x squared plus y squared minus 1. So this is the backwards of the map that I just drew here. So there's x. And here's s. Okay, so we're mapping down. And then we had a point 0 here. So this was 0. And then I wanted to look at the fiber above this thing. Okay, and what I said was that this fiber here, okay, what I said was is that this thing here, right, should be the tensor product of this, right, with this map, okay, over this map. Okay, so let me just write out what that is. So according to our definition, so f inverse of 0, f inverse of 0, this is what I said. I said it was okay, so what did I said it was the fiber product. So this was x over s with t, okay? And according to our thing, this is like c of xy, x squared plus y squared minus 1. So I'm kind of writing the tensor product a little backwards. This is the x part, right? And then this is over, so s with c of x. Okay, and then I'm tensoring with C, okay? But I'm tensoring with C with respect to this map 0 star, okay? So another way to think about this thing here is this thing here is really C of x mod x, okay? So that's another way to think about this side over here. So we're really modding out by this ideal here, okay? And so what does this become? Okay, so this is, you know, this is A, this has the form A tensor R mod I. Okay, and then by our theorem, this was A mod IA. Okay, so if we were going to mod out, we'd get this. So this, what is this thing? So we're just modding out. So this is telling us is that we mod out by X as well. Okay, so this thing here. So here we're writing X as spec A. Right. Okay. Here's A.
Which theorem was that from?
So this is the thing about that I said at the very top, like at the very beginning of class.
About flat module.
Yeah. So like here, if you tensor with you know, tensoring by modding out is really the same thing as M mod IM. Okay. And where are we? Back. Okay, so this is M mod IM, and so okay, so what is this thing now? So this is C. Oh, Okay, so what is this thing? So this is C of xy, okay, mod, okay, let's just write this out, x squared plus y squared minus I, mod, okay, and now we're doing the ideal x times C of xy mod x squared plus y squared minus 1. Okay, so we're doing this whole thing. Okay, and so what is this? So this is really just the top thing modded out by x. Okay, so this is the same thing as the top thing, you know, modded out by this extra x. And what is that? So this thing is really just C of y. Okay, and we just kill all the x's, y squared minus 1. Ah, what's that? So that is C of y over y minus 1, y plus 1. And then way back, way long time ago, right? We showed that this was from the Chinese remainder theorem. Y plus 1. Okay, and so from this part, you see that we have a direct sum here. Direct sum, what does that mean in terms of schemes? So this is one copy of C. This is isomorphic to C. So this is isomorphic to C cross C direct sum C. So we have this ring. Okay, direct sums mean connected components, right? If you have idempotents, right, that was what this motto was. Idempotents give connected components. We have two connected components, right? And these are our two connected components, which are the fiber. Okay, so what we did is we took this drawing here, right? And I showed you that if I did this inverse image definition using the tensor product, that it performs like we want. Okay, it gives you the fiber. Okay, and that's kind of cool. Okay, so we define, in terms of schemes, we define the fiber this way. We define the fiber of a map to be the tensor, to be the fiber product here. And to compute it, you do all this tensor product stuff, right? And we use this, and then we broke things down using Chinese remainder theorem. But we can see that, that the thing that we get is the two fibers. Pretty cool, huh? Right. It's also cool because, like, now you have a geometric way. Suppose you have a family over the integers. Okay, so you have some equation. Oh, we can do this. Okay, so let's do another example here. Suppose we replace C of x here. So let's just do this. Okay, so let's replace C of x everywhere with z. Okay, so let's replace everywhere with z. So this is going to be z. Okay, and instead of t, I'm going to do spec of fp. Okay, so and then this map here will be the reduction mod p. So this will be reduction mod p. Okay, and so here we go to n maps to n mod p. Okay, so we have this thing. Okay, and instead of this, we would have spec z y. Okay, and okay, and then we could do something here. I don't know. We don't really have a variable here, but I guess we could do y squared minus 1. Okay, so we have. I mean, we could do. I mean, what do we want x to be? Do we want x to be something more interesting? We can do another variable too. But when we do another variable, it's like adding a dimension. So let's just do another variable. Let's do it like this. Okay. So the map here then is given by z. In this case, z goes to z of x, y. This is the structure morphism. So what I'm describing now is this vertical map here. Okay, and then if we were going to do all this, okay, so I compute the fiber product. The fiber product would be like this again. I mean, I don't like really the name 0 here anymore, but whatever. We can still compute the fiber. So give me your favorite prime. Well, I mean, I guess we don't need to do it for a particular prime. We can do it for all primes at the same time. But now this thing here, what does it become? So it's spec of, okay, now we have z of xy over x squared plus y squared minus 1, tensor over z with the map. Okay, we called it 0 again. I don't really like that name, but whatever. You can call this map whatever you want. And then we had this with, okay, and then we had the point. So we did FP, which was Z mod P. Okay. And so when we do this, this turns out to be spec of, and then we just reduce the coefficients here. So when we're base changing here, so what we're doing is we're base changing by a finite field, you get, so this is FP xy over x squared plus y squared minus 1. Okay, so yeah, so what we're doing is we just what happens is, okay, so what happens is that we have, okay, so we have spec z down here, and then at each fiber we have the reduction of this. So at every prime here, so this is the circle. So this is 2, 3. Okay, so this is so this one actually turns out to be a double. Okay, so this one, let me draw this one, kind of funny. Okay, so there's this one, and then there's a bunch of circles here. Okay, so this thing, here's x and here's spec z, and so what this, each fiber here above each of the points, this is the reduction of x mod p, right? And so what we've done is we've made a family, and then if I each one of these points on the bottom is this one of these maps where you take the integers and you reduce it mod p, right? And then the fiber above it, right, is it is the the reduction of it's this equation, right? So this thing is this thing here, right? And I guess this is for 7 or something, right? Okay. Why? Okay, so here's a question. Why did I draw this one? Why did I draw the 2 one all weird? Okay, so the 2 one's all weird because of this. So F2. Let's just do the F2 case, and then I'll let you guys go. So we do xy. Okay, and so we have x squared plus y squared minus 1. Okay, so what is that? So this is F2 of x, y. And then we have this non-reduced thing. So this is x plus y minus 1 squared. So it turns out that this is just a line, and the line appears with multiplicity 2, right? Because it's a non-reduced thing. And so you kind of have this family, and it's going along nicely, and then here you just get this like thing that's like it's like a line, but it's like a double line because the equation is to a power. Okay, so yeah, and so that's how we draw this example. Yeah, so I guess one other comment that you can do is that you can formulate intersections of open sets via fiber products. So that's incredibly useful too. And I guess next time I will move on to local properties. So local properties of these things, so that we can do that spoilery thing. Okay, so just a reminder, the exam is in the files, and I am going to stick around for questions if you guys have any.
Thanks. See you, Taylor.
See ya.
Thank you.